So the difficulty is, first of all, trying to prove that these two triangles are similar. That's the challenge. So what three ways did we learn, hopefully that you learned, that you can prove that two triangles are similar? What's one of the ways? Two of them really straightforward. It's one of the ways. Cecina.
Divide 6 by 3. Divide 6 by 6. See if they all equal the same number.
Ratio.
Okay, so we take the ratios of all the sides. So we know that here, FE is twice as long as BC. But we don't know anything about this length and that length. We don't know anything about this length and that length. So we can't use all three sides to check. Okay, but that is one way we could do it. What is another way that we could prove two triangles are similar? What is the second way? Well?
The angles, comparing the angles.
Yeah, if all the angles of the triangle are the same, then again, there will be similar triangles. So we know that these two are both 59. Well, we know this is 90, but do we know anything about the angles of this triangle? No, stuck again.
But we know that the angle is
This?
for the other angle of 31 is 31.
Okay, so we know that this is 31. Good. So you got 31 because you did the 180-degree triangle rule, right? Whereas angles of a triangle out to 180. So 180 minus 90 is 90, minus 59 gives us 31.
Right.
But we don't know anything about the angles of this triangle, and that's a problem. So we can't use that one, right? A lot of us think that, well, these two angles are the same. There's nothing that we've done that proves that. They're not opposite angles. Okay? There's nothing that we've done that's shown that they're the same. What do you notice about this triangle though? The fact that it's a right angle triangle. How many sides do we know? 2. So can we get the third?
Yeah.
Oh, so let's start off with that. How do we get off? How do we get the like the third one? Sorry? Yeah, so we take the square of each of the short sides and we add them together. Take the square root. That'll be. So here we got 5 squared is equal to 25. 3 squared is equal to 9. So here I need the square root of 25 plus 9 is what?
35.
Square root of 34. Cool.
Oh,
So we got the length. So always when you're given a problem, take what you have and try to find something else. Right? So here we're given a right angle triangle, only given 2 lengths, we can find the third. Oh, now as soon as we got that, we got some eyes light up. Cena.
So now that we have the square root of 34, you know that that is the long one on the big triangle would be 2 times.
Okay, so first of all, you pointed out already that FE is twice BC, right? So the ratio there is 2. Now what are you saying? Square root of 34 multiplied by 2? What? We just look at the ratio of FA. Adrian?
There's a rule that says when 2 sides are in proportion, their angle is their intended angle is equal. So
Yes.
then you have all your sides are in proportions.
Okay, so now that we know that these two sides, right? So we know that lengths of these two sides. Can we compare them?
Yeah.
So let's compare FA. Well, that's really 2 times bigger than AB, right? 2 times the square root of 34 is 2 times bigger than square root of 34. So we get it's 2 times bigger than AB. Right? So those 2 lines or those 2 sides are proportionate. So as Adrian was saying, if we have 2 sides of a triangle that are proportional and the angle in between them is the same, then they are similar triangles. That was the third way that you could prove that they're similar triangles. So is the angle in between them the same?
Yeah.
How do you know that?
No.
No?
The sides are the same?
How do you know the angle between those two sides are the same?
Because
The angle.
Because
I told you.
they equal.
It's 59. It's 59. The angle between the two sides, right? We have one side here, one side here. What's that angle? 59. This side here and this side here. What's the angle? 59. It's the same.
But you just said that we don't know for sure.
I told you it's 59 and it's 59.
So
And
that's
it's
it?
between the two sides. And it's in between the two sides that we know are proportional. We don't need this side. Right? Does everybody see that? Right? You hopefully did an exercise on that of saying that if the angle between two proportionate sides are the same, then its triangles are similar. Okay? And angle EFA is equal to angle ABC. Therefore, the two triangles are similar. Not like writing on this one. So now that we've proven that the two triangles are similar, what's the length of EA?
10.
10. Right? Because this triangle is basically twice, the sides are twice as long. So this is just 10. Now can we say that this is 90 degrees? Yes, because they're similar triangles that have the same angles. And now we can show that these two are indeed the same as well. Okay? So sort of there's one question to sort of summarize a little bit about what we needed to grasp from those last two lessons, right? Understanding proportions, understanding similar triangles, and using the Pythagorean theorem.
Fun. It's so fun.
Any questions to this? This one?
So the three ways were compare the sides.
All three sides,
Compare
yes.
all three sides, compare all the angles.
All
and
three
What
angles.
was the third one?
Third one is you have to find the two sides of a triangle. So here we got two sides, here and here, right? If those two sides are proportional to another two sides of your triangle, the other one, and the angle in between is the same, that's how you can show that they're similar triangles. So two sides and the angle in between. I think that was method number 2 in the Google Doc handout.
Any two sides?
Any two sides and the angle that's in between.
So, but like the same two sides of both triangles. So,
As long as they're proportional,
yeah.
right?
And between the two sides, the angle.
And the angle has to be the one that's between the two sides. Or in between them. Okay? Audrey had a question of where the square root of 34 was coming from.
Yeah.
Do you understand it now? Okay, on to the new lesson, which is really a review of grade 9. So I want you to graph this linear equation. Y is equal to 2/3 x. We had to do that even back way in Unit 1 when we solved systems of linear equations. Graphing lines. So graph, and make it a rather large one, because we're going to do something with it. So everyone want graphing paper? Yeah, I'm not sure I have enough to roll out.
Thank you.
Anybody else?
I can prepare.
Anyone else? One last one?
I'll take it.
So I'm reporting it.
Sir, I'll take it. Even though I don't have it. Thank you, sir.
It's not on blackboard, it's on the top.
So pretty much grand.
So graph our equation y equals 2/3
I
x.
forget.
Oh, I know how to do this.
How do we graph a linear equation?
No, it's.
Oh,
Sure. Good. But this is a linear equation.
Wait.
So all you need is 1 point
Wait.
come on.
of what else do you know? What's special about this number here? The 2/3. What's special about the 2/3? Remember why slope, y-intercept form? I just taught this in grade 9. I go back and play the video of my last class right now if you want to refresh your memory. Right? In 10 minutes, so I gotta get heard.
Wait, is it? No.
Okay? So this is really, remember slope, y-intercept form, but plug in x is equal to 0, what's my y value? 0, right? 2 times 0, 2/3 times 0 is 0. So it goes through the origin. What's my slope?
2/3.
So that means what?
2 to the right.
Oh, 2 up.
2 up, rise,
Oh, right.
3 to the right.
So it starts at 0, 0. Wait, why?
Okay, so your line should look something like that. Who drew a parabola?
I might have drawn a parabola.
Do you feel like you're going backwards and making you crawl now that you're also experts in quadratic functions? You gotta go back to know straight lines.
Wait, why is it starting at 0, 0?
Because if x is 0, so what's the value of y?
0.
So plug in that equation, x equals 2/3 times 0. What's y?
It's just 0.
Yeah, so that's 0 comma 0. So if I was to draw this line, pay attention up here please. I know that seems trivial now. I need you to focus up here. This is demonstrating a concept that you're trying to get through in 10 minutes. So I start with 0, 0. I'll label it. So I went up 2, across 3. Got another point over here. Having 3 comma 2. Then up 2 across 3, I got another point here, which would be 6 comma 4. And then over here would have been 9 comma 6.
Bye.
Okay? So I'm going to plot those points through my line. I'm going to do something with this that might amaze you because it's so awesome. I'm going to make a triangle of this.
Oh no. Oh my god.
Yo, that's a percent.
Okay? There's a triangle.
Oh.
So all I did was just take that point, go straight down to my x-axis and straight across to the other point. So I know for sure that this is a 90-degree angle. Right? Just how I defined how I made that line. So without taking out calculators, because nobody loves our calculators, give me the length of 2 sides of this triangle. Give me the length of 2 sides of this triangle. Cecina.
3 and 2.
Whoa, that was kind of easy. Which one's 3, which one's 2?
The bottom.
The bottom's 3?
Side.
Okay. So everybody see how we got the length of those triangles? Okay. So I'll amaze you again by drawing yet another triangle.
Oh my god, David Blaine. That's
Okay, you know what? If you guys find this easy, good, but stay with me so that you get the concept afterwards. So what are lengths of two of this triangle, two sides of this triangle? Audrey. Which one's 4 and which one's 6?
6
So the one across,
and 4.
okay? And I could do this yet again with a larger triangle up here. And this would have been 6 and 9. So let's focus on those first two triangles. The green one and the red one, are they similar?
Yes.
They're all.
Why you say so yes so fast? How do you know that they're similar? How do you know they're similar? See that?
Two sides, 3 and 2 and 6 and 4 are proportional.
Okay, so we're gonna do this one, right? So we just do the vertical side. You know why I tick Marcus? Just based on the conversation you're trying to have with me before this class of why things were difficult before. I'm starting to understand why now. So I'm going to take the side that's vertical 2 over the side that's horizontal. So that's my ratio of those two sides, 2/3, right? With the red one, what's the ratio of those two sides? Well, it's 4 over 6, which is really 2/3, right? And what's the angle in between them? 90 and 90. So that's how we prove that those two triangles are similar. Pretty neat, huh? What have we noticed though about these numbers here? It's their slope. We just did the rise over the run. It's just our slope. Right? We have that ratio there. Rise over run. Just by doing that, we know that those two triangles are similar. So what we're going to notice is, we'll hopefully notice, is if I take that one triangle and I blow it up. Okay? I'm on the wrong slide. There we go. Okay? So if I blow this up, that's what that largest triangle looks like. I got 9 along the bottom, 6 across the top. So what I do is I do prefacing my notes, right, with a star, exclamation mark. These are the key concepts you need to understand in this lesson. In other words, write them down. Know it. So here, let's say the angle theta, so this is a Greek letter, theta, and it actually looks like this. It's almost like a little O with a line across. Angle theta is referred to as the slope angle. So this angle here is referred to the slope angle. Which is opposite of the rise. So which is our rise over our triangle? It's this one here, right? Because it's up and down. So it's opposite the rise and adjacent to the run. Okay? So finish the first point first. So I want to make sure that we understand this notion of opposite and adjacent. You can also look at your angle here, right? So our angle is here, and this triangle, the opposite side is easier to pick off, right? It's the side that's farthest away from this angle. So that's going to be this side. So this side is the opposite side. And we'll label this for short, just O, the opposite side of that angle. Tricky part is the adjacent side. That is the side that is beside or closest to this angle. Well, there's really two of them, right? But we know that this one has a special name already. What's this one called? Hypotenuse. Right, and we'll just call it H for short. So opposite and adjacent will never be the hypotenuse. It's already got a special name. So by default, this other side that's closest to this angle is the one that's the 9. Right, so that's the adjacent. And we'll denote that as A for adjacent. Okay? So what the next line is saying is that the tangent of theta is the ratio of the opposite side to the adjacent side in a right angle triangle. That's the same as saying tan of theta is opposite over adjacent. That's right. We'll talk about that next time. Just look just from this diagram, right? We'll talk about this angle here. So in this specific case, tan of theta is what? Well, it's opposite over adjacent, which is what? What's the opposite side? 6 over 9 is 2/3. So tan of theta is 2/3. That's the ratio of the opposite side to the adjacent side. Okay? Redfish writing this?
No.